Inside your skull sits 3 pounds of wet, organic tissue, an electrochemical network firing billions of impulses every single second. For centuries, classical neuroscience has modeled this system as a digital machine. Individual neurons are viewed as biological logic gates, processing inputs and outputs through a deterministic electrical code. But modeling the brain as a complex computer leaves a gaping logical vulnerability. A digital computer can process visual data and execute complex physical movements while remaining completely dark inside. If our brains are strictly hardware running deterministic scripts, there is no physical reason for the presence of internal awareness. Classical Newtonian physics gives us a brilliant instruction manual for the gears of the biological machine, but it lacks the conceptual toolkit to explain the subjective observer experiencing the world from the inside. To find behavior that isn't strictly predetermined by a rigid mechanical code, we have to look past the macroscopic world and down to the subatomic scale of quantum superposition and wave function collapse. In the early 1990s, mathematical physicist Roger Penrose proposed a radical alternative. Because human thought can perceive mathematical truths that exist outside formal algorithms, he hypothesized that the brain must rely on the non-algorithmic rules of quantum mechanics to generate the human mind. The proposed hardware for this process sits deep inside our cells. Running through the interior of every neuron is a structural scaffolding grid composed of hollow polymers called the microtubule network. But the physics community quickly pointed out a massive physical obstacle. To maintain a delicate quantum superposition in a laboratory, experimental physicists have to lock their qubits inside highly shielded cryogenic units, cooled down to a fraction of a degree above absolute zero. This chart compares timescales of standard biology against quantum decay. Physicist Max Tegmark calculated that inside the warm, wet brain, a quantum state survives only a fraction of a picosecond before destruction by thermal noise. Meanwhile, a single neuron takes a full millisecond to fire. The math suggests a stark physical contradiction. According to standard decoherence formulas, the brain is too warm and too noisy to support the delicate superpositions required for quantum computation. For quantum mechanics to survive inside the brain, nature needed a biological method to bypass this thermal noise. In 2015, physicist Matthew Fisher identified a specific atomic loophole. Previous calculations focused on the outer electron shell of atoms, which is highly exposed to external heat. Fisher shifted his focus deep into the core of the atom, looking at a property known as nuclear spin, which sits shielded behind a dense electron cloud. He isolated phosphorus-31. It is a highly abundant biological element that possesses a low nuclear spin of exactly 1/2, making it an exceptionally well-insulated quantum bit. These entangled phosphorus atoms are packaged with calcium ions into Posner molecules. The outer shell blocks electrical turbulence, acting as organic Faraday cages. Protected inside, the quantum state's survival time expands from a picosecond to hours or days. This model suggests the brain relies on an evolved fleet of chemical shielding capsules, capable of protecting fragile quantum information while navigating the warm, wet chaos of life. We already have evidence of nature leveraging these mechanics. Migratory songbirds navigate the planet by utilizing entangled electron pairs inside their retinas, which allow them to physically see the Earth's magnetic lines. The testing ground for human quantum consciousness lies in a century-old medical mystery, general anesthesia. We have used gas to switch off the human mind for generations, but the exact molecular mechanism was always unclear. Quantum neurotesting has tracked these anesthetic molecules as they migrate directly into the hydrophobic resonance pools deep inside the microtubule network. The presence of the gas halts electron mobility within the core scaffolding of the cell. This causes the microtubule's capacity to support global quantum coherence to collapse. This suggests a functional correlation. When we artificially target and block the brain's quantum processing capacity, the conscious observer instantly unplugs, even as the physical machine remains alive. Moving the mind into the quantum substratum requires us to abandon the view of humanity as a passive, predetermined meat computer. This shift points back to dual-aspect monism, a framework championed by physicist Wolfgang Pauli. Working with psychologist Carl Jung, Pauli proposed that internal subjective consciousness and external physical matter are two complementary aspects of the exact same underlying quantum fabric. In a classical universe, every thought and action is the inevitable result of prior particle collisions. But by introducing the indeterminism of wave function collapse, the quantum framework breaks this rigid chain of predeterminism. If the brain is actively orchestrating these collapses through its microtubule or phosphorus networks, it provides a physical mechanism for genuine choice to enter the material world. Human intent functions as an active causal force in this model. It is the integrated bridge through which the universe calculates and collapses its own mathematical possibilities into objective reality.